Let us talk about systems of particles. In this case, we're going to start putting everything together. We are going to analyze systems that have a constant mass, that have forces, and we're going to see in this particular chapter that we can have external forces and we can have internal forces. So we mostly talked about external forces, such as gravity, which is a vector. And if you remember, gravity is easy to visualize as a vector because if it's only in an XY Cartesian coordinate system, if you're falling, if an object is falling, then the gravity is a negative value in the y-axis, x horizontal, y vertical. But if you have slope, like an inclined plane, gravity has components with respect to the angle, and we remember n x and y, cosine, sine, etc. In this chapter, we're gonna see internal forces, and internal forces are forces that you have inside the system when you apply external forces. So, or even if you don't apply internal forces because of chemical energy, there's an explosion, then there's internal forces because of displacements and stress and strain. So internal forces and external forces. All that is going to be applied on the boundary and inside the volume of the object. And it's going to be a very interesting case when you see everything applied because we're going to keep the mass constant, we're going to have the forces, and in that case, we'll see how the summation of the forces is going to be equal to the mass times acceleration. So mass could be the whole system depending on what are you trying to analyze, because this could have an angular velocity, you're going to have reactions here, you're going to have a weight because of the people and the structure, you're going to have reactions here and here, and then internally there are going to be internal forces keeping the structure from collapsing, and internal forces here. And if you took statics, you know that you can analyze the internal forces also. So we've seen every single thing that we know that we need to put everything together in this chapter. We know Newton's law that a body that is at rest will stay at rest unless another force or another body is going to push it or change that state. We know the law that tells us that the forces are equal to the mass times acceleration, and we know the inertial law where a body that is moving will keep moving in an inertial frame of reference unless there's something that is going to keep it from moving. We know that. We know linear angular momentum. We talked about that in chapter 12. Mass centers. We know how to capture the mass centers is because of the gravity constant. Angular momentum, we talked about that. Conservation of mass and momentum and energy is very important. So we know this concept. We talked about kinetic energy, they're called T. Work principles and conservation for energy. We know that the change in internal energy is because of the change at the states, because of the energy of the states. So at state 1, you have something going on. Say the engine is off and the piston is not moving, and at state 2 the piston is moving at 2200 rpms, for example, and we want to know what is the velocity of the piston or what's the power, the torque, things like that. And we don't care about any story, we don't care about the history, we don't care about any details of how the engine went from being at rest to being at the state at which we want to study. If we wanted to study that path, we will have to go back to kinematics. Okay, But since we only care about point 1 and point 2, we're going to take, at this point, there's zero velocity of the piston, for example. At this point, the velocity has to be known, but we know that the RPMs are, etc., etc. We know how to get from that information that we have at the states, we know how to compute the energy that we need. And that's T and T2 and T1. Remember that T, energy, kinetic energy, is 1/2 of the mass of the system, the piston or the whole system, times the velocity of the system squared. If this is I. So T1 is going to be velocity 1, at T2 is velocity 2. The mass is conserved. Notice that it will be much more complicated in thermodynamics when the mass is not conserved. If you have combustion and in theory the mass is conserved but went from liquid, gas, and a bunch of things in the air like oxygen, nitrogen, to a combustion effect, right? So in this case, you're going to have to use chemical energy, which is mu. But don't worry about this. In this chapter, we're talking about solid bodies where mass is conserved. All right. So this is just examples telling you that this approach of energy is used for problems where things are very complicated. So you only care about certain points, point 2, point 3, point 1, everything is at rest. At point 2, there are some information that we know, some distances, the mass is known. At point 3, you're probably coming back or changing to a different velocity, but we don't care about how we got into that path or how the geometry of the movement and accelerations are determined. We only care about the states. All right, that's the energetic approach. All right, so if you go to your chapter 14, we're gonna notice that again you start from a system of reference. In a 3D system of reference, R3, you have, say, there are a bunch of particles or a big system where you know the distance of that system with respect to some origin. So the distance of the Earth with respect to the Sun, or the distance of a car with respect to a coordinate system, etc. The system on an airplane, with the satellite with respect to Earth, whatever. The equations that are going to be studied are the external forces, as we said a minute ago, and the summation of the internal forces. So if you keep going into engineering degrees and you take mechanical engineering, civil engineering, you'll see that the internal forces are going to be take any object, a cylinder, a column, a beam, a rectangular shape, a car, whatever. Once you apply external forces to it, like a bridge, you start deforming it. Internally, you're going to have stress and strain. We won't compute them in this chapter, but they are all related to the forces, okay, external forces. And they're going to produce internal forces that are going to try to either compress or stretch. That's where in statics we computed compression or tension. We only cared about the magnitude of the tension and the magnitude of the moment, but internally you're going to have something called elasticity or plasticity. And that basically means that if you apply forces or stresses to a system, and after you take the stress away or the force away, the system comes back to its original volume, its original shape, then it's an elastic behavior. If it doesn't, if it breaks, if it cracks, if it stays deformed, kind of like a plastic bottle that you twist too much and then it stays deformed, you crush it like a aluminum can, then that's called a plastic deformation. All right, so these equations are the entry-level equations to determine how the body is being deformed. Because remember that F equals ma is a second derivative. acceleration is the second derivative of the displacement. You remember this guy? So once you find the acceleration, you can take that and go back to a kinematic approach and determine things that you want to find. So this is a powerful approach right here. Again, if you want to find momentum, sorry, in this case, it's not momentum. Remember, momentum is mass times velocity. If you want to use the moment, moment is distance times a force, then you can definitely use the conservation of moment in this case. All right. So this is just more forces saying that more equations telling you the same thing. You can actually be very specific and capture forces in different directions. And now you start to see how everything comes together. So the momentum is going to be the contribution of every single mass in the system times the velocity of every single element in the system.